All right, today we're looking at the Unit 7 Kinetics AP Chemistry worksheet. For number 1, we're looking at what is the delta concentration of NH3 over delta time in respect to that of H2. And so when we look at these, our rate is going to be negative for our reactants, and we're looking at the reciprocal of those coefficients. It's positive for our product. Okay, and then we're only focusing on NH3 and H2, so we can kind of ignore nitrogen here. I'm going to start with my NH3, and so my rate for NH3 would be equal to 1/2 delta concentration of NH3 over delta T. That would be equal to negative 1/3. Oh, that doesn't look like a 3. Let's change that. Negative 1/3 the change in concentration of H2 over delta T. And so we have to get rid of that 1/2. In order to do that, we just multiply both sides by 2. And so we get an overall delta concentration of NH3 over time equal to negative 2/3 the delta concentration of H2 over change in time. Okay, so that's our answer for number 1. For number 2, 3, and 4, we just had to kind of remember that chart. And so we're just listing this information. It says give the integrated rate laws. Now the integrated rate laws are on your AP resource, but they don't tell you for which order of reaction they go with, and so you'll have to know what to do with them in that sense. But for a 0 order, we know our integrated rate law is the concentration of A minus the initial concentration of A, and that would be equal to our negative K times T. Okay, for our first order reaction, we have the natural log of the concentration of A minus the natural log of the initial concentration of A equaling negative K times T. And then for our second order reactions, we have 1 over the concentration of A minus 1 over the initial concentration of A. And that one, remember, is just equal to KT, not negative KT. Okay, remember when we use our integrated rate law is when we have elapsed time given to us in our problems. That's when we need those integrated rate laws to solve for those problems. Okay, so number 3, give the half-life equations. Okay, the first order one is on your resource because we use that for radioactive decay. And so our T sub 1/2 is equal to 0.693 divided by K. The 0 order reaction half-life we have to memorize. That one is not given to us. That's equal to T sub 1/2 equaling the initial concentration of A over 2 times K. Oh, that's really messy. Here we go. For our second order half-life problems, we have T sub 1/2 equal to 1 over K times the concentration of the initial A. Okay. What graph would give you a straight line for each of the following? If we plot for a 0 order graph, a 0 order reaction, and we plot concentration of A versus time, it gives us a linear graph. Okay, for a first order reaction, we would have to plot the natural log of concentration of A versus time to see that straight line. And then for a second order reaction, it would be 1 over the concentration of A versus time to see a straight line. And remember, from those straight lines, we can then calculate the absolute value of the slope, and it gives us our K value that we need for rate law. Okay. How would you determine the instantaneous rate at time t from a graph of concentration versus time? You would have to find the slope. of a line drawn tangent to the curve try that again. Find the slope of a line drawn tangent to the curve at time t. Okay, and that would be equal to the instantaneous rate. And we can do that for reactants or products on that graph. All right, number 6, the conversion of cyclopropane to propene is a first order process. If we begin with 0.0200 molar cyclopropane and find that after 168 seconds, the concentration of cyclopropane is 0.00286 molar, what is the rate constant K? Okay, since we see that elapsed time, we know we're going to need our instantaneous rate law. And since it's first order, my instantaneous rate law is natural log of the concentration of A minus natural log times the initial concentration of A, and that equals negative K times T. Again, less messy. Here we go. Okay, so our concentration of A, natural log of that, 0.00286. Oh, goodness. It's so laggy. Let's try that again. All right, so we have the natural log. Okay, our final concentration is the 0.00286 molar. From that, we'll subtract the natural log of our initial concentration, which they say is 0.0200 molar. We're solving for K, and our elapsed time is 168 seconds. Okay, so when I type in the natural log of my concentration minus the natural log of my initial concentration, I divide that by 168 seconds, and I take the inverse for that negative K. I get a K constant equal to 0.0116, and then my unit there for K should be inverse seconds. Okay. Last one for today is number 7. Okay, we have a reaction there. They tell us it's a second order reaction. They give us a K value of 25.0, inverse molarity, inverse second at 420 Kelvin. They give us an initial. Okay, so there's an initial concentration of HI, and they're asking us what would the half-life be for HI. So since this is a second order kinetics reaction, we know to find half-life, our formula would be T sub 1/2 equaling 1 over our K constant times the initial concentration of A. And so our T sub 1/2 will be equal to 1 over our K, which they tell us is 25.0, times our initial concentration, which is the 2.00 times 10 to the negative 2. And so I type that all in my calculator, and I get a half-life equal to 2 seconds.